You are floating in space, 60 million kilometers from the nearest black hole, when your ship's engine fails. There is no explosion, no warning klaxon, just a quiet shudder through the hull, and then silence, and then the slow, inevitable realization that your trajectory has already been set. You are drifting, and you are drifting toward Sagittarius A-star, the supermassive black hole at the center of our galaxy, and there is nothing you can do to stop it. You have several hours before anything interesting happens, then several days. Then, finally, you cross a boundary that no signal, no light, no information of any kind has ever crossed and returned from. You cross the event horizon. Let's talk about what actually happens to you. Because the reality, according to physics, is far stranger than being crushed and far more unsettling than simply dying. The first thing you need to understand is that the event horizon is not a physical surface. There is no wall, no membrane, no barrier you can feel yourself pass through. Physicist Kip Thorne, in his work on black hole physics that helped earn him the 2017 Nobel Prize, has described the event horizon as a point of no return, defined purely by geometry. The boundary beyond which the curvature of spacetime is so extreme that even light, moving at the fastest speed the universe allows, cannot escape back outward. From your perspective, sitting in your ship crossing this boundary would feel like nothing at all. No jolt, no sensation. You would look at your instruments and see nothing unusual happening locally. But something has already happened that you cannot undo. Physicist Roger Penrose, who shared the 2020 Nobel Prize in Physics for his mathematical proof that black holes are a robust prediction of general relativity, demonstrated that once you cross the event horizon, all possible future paths through spacetime, every direction you could possibly travel, no matter how you accelerate, no matter what you do, lead only toward the singularity. This is the part almost no popular explanation gets right. Inside a black hole, the singularity is not a place you could avoid by steering around it. It is not a location in space at all, in any sense you're used to. It is a moment in your future, as inevitable as next Tuesday. You cannot avoid your own future any more than you can avoid getting older. The second thing that happens depends entirely on the size of the black hole, and this is where most science fiction gets the drama badly wrong. For a black hole, the mass of our sun, physicist Kip Thorne and others have calculated that the tidal forces near the event horizon would be so extreme that a human body would be stretched vertically and compressed horizontally within a fraction of a second, a process astrophysicists have informally termed spaghettification, a term popularized by physicist Stephen Hawking in his public lectures. Your feet, closer to the singularity, would experience dramatically stronger gravitational pull than your head. The difference would tear you apart at the molecular level before you were even fully across the event horizon. Death, in this scenario, would be almost instantaneous and would occur before you crossed the point of no return. But Sagittarius A-star is not a small black hole. It has a mass roughly 4 million times that of our sun, and the physics of supermassive black holes work dramatically differently. Astrophysicist Andrew Hamilton of the University of Colorado Boulder, who has produced detailed simulations of what falling into different sizes of black holes would actually look like, has demonstrated that for a supermassive black hole, the tidal forces at the event horizon itself are gentle. Gentle enough that a human being could cross the horizon fully intact, feeling nothing unusual, and continue falling for a significant period of time before spaghettification eventually occurs deep inside, much closer to the singularity itself. This means that if you fell into Sagittarius A-star specifically, you would survive crossing the point of no return. You would have time, measured in minutes according to Hamilton's calculations, to look around, to think, to understand exactly what has happened to you before the tidal forces finally became strong enough to kill you. What would you actually see during those minutes? This is where the physics becomes genuinely strange, because your experience and the experience of anyone watching you from a safe distance would diverge in ways that seem to contradict each other. And reconciling that contradiction was one of the great achievements of 20th century physics. From the perspective of someone watching your ship fall toward the black hole from a safe distance, you would never actually appear to cross the event horizon. Physicist Karl Schwarzschild, who in 1916 produced the first exact solution to Einstein's equations describing a black hole, demonstrated mathematically that as an object approaches the event horizon, the effects of gravitational time dilation become so extreme that, from an outside observer's perspective, your clock appears to slow down and your image appears to freeze, growing dimmer and more redshifted, approaching the horizon asymptotically, but never quite seeming to touch it, stretched out over what would appear to the outside observer to be an infinite amount of time. But from your own perspective, inside your own reference frame, none of that delay exists. Physicist John Wheeler, who coined the term black hole in 1967 and worked extensively on the theoretical implications of gravitational collapse, emphasized that general relativity is fundamentally about the fact that different observers experience time differently depending on their motion and their position in a gravitational field. And neither perspective is more real than the other. From your seat in the ship, you would cross the event horizon in a perfectly ordinary, finite amount of time. Seconds or minutes, depending on your trajectory. The person watching from outside would never see it happen. Not because it does not happen, but because the light carrying that information would take longer and longer to reach them, forever. You and the outside observer are both correct. You have simply stopped being able to communicate the same version of events to each other. Once inside, looking back the way you came, you would see something extraordinary. Physicist Andrew Hamilton's simulations show that the entire history of the universe outside the black hole, every photon of light that will ever fall in behind you, compressed by the extreme gravitational lensing near the horizon, would appear to rush past you in a bright, distorted ring, a visual compression of the external universe's remaining lifespan, streaming past your position before the singularity ends your ability to perceive anything at all. You would, in some meaningful sense, be watching the future of the universe outside compress into your final moments. The third thing you need to understand is what actually happens at the singularity itself. And here, honest physics has to admit something uncomfortable. We do not know. The equations of general relativity, when extended all the way to the singularity, predict a point of infinite density and infinite spacetime curvature, a mathematical breakdown rather than a physical description. Physicist Stephen Hawking and mathematician Roger Penrose, in their singularity theorems developed in the 1960s, proved that under very general conditions, the formation of singularities is an unavoidable consequence of gravitational collapse according to general relativity. But both Hawking and Penrose were clear that this mathematical prediction almost certainly signals the breakdown of general relativity itself in that extreme regime, rather than describing what is physically actually there. Physicist Carlo Rovelli of the Centre de Physique Théorique in Marseille, a leading researcher in the field of loop quantum gravity, has argued extensively that a genuine theory of quantum gravity, a unification of general relativity with quantum mechanics that physicists have been pursuing for nearly a century without complete success, would likely replace the singularity with something else entirely. Rovelli and collaborators have proposed models in which the extreme density inside a black hole triggers a quantum bounce, transforming the collapsing matter into an expanding region, a white hole, theoretically the time-reversed twin of a black hole, rather than crushing it into a true infinity. This remains speculative. No experiment has confirmed it, but it represents a serious scientific possibility that what you would experience at the end of your fall is not annihilation into a mathematical infinity, but transformation into some other physical state entirely, one that our current theories cannot yet fully describe. The fourth thing worth understanding is what happens to the information that made up you. This question, known as the black hole information paradox, occupied physicist Stephen Hawking for much of his career and remains one of the most actively debated problems in theoretical physics. In 1974, Hawking demonstrated that black holes are not entirely black. They emit a faint thermal radiation, now called Hawking radiation, caused by quantum effects near the event horizon. And this radiation means that black holes slowly lose mass and, over unimaginably long timescales, eventually evaporate entirely. The paradox is this. Quantum mechanics insists that information cannot be truly destroyed, that the complete physical description of anything that falls into a black hole must, in principle, still exist somewhere. But Hawking's original calculations suggested that the radiation emitted as a black hole evaporates is purely random, containing no information at all about what fell in. If that were true, then everything that ever fell into a black hole, including, eventually, you, would be permanently and completely erased from the universe when the black hole finally evaporates, an outcome that would violate one of the deepest principles of quantum physics. Physicist Juan Maldacena of the Institute for Advanced Study, along with other researchers working on what is called the holographic principle, has produced theoretical work suggesting that information is not actually lost, that it is somehow encoded on the event horizon itself, or subtly imprinted in the correlations of the Hawking radiation in ways that are not obvious but are, in principle, recoverable. Hawking himself, in 2004, publicly conceded a long-standing bet on this question, agreeing that information is likely preserved, though the precise physical mechanism by which this happens remains, even now, an unresolved and actively researched problem at the frontier of theoretical physics. This means the honest answer to what happens to you, at the deepest level, is unresolved. Something about the complete physical information that constituted you may, in some transformed and almost certainly unrecognizable form, persist somewhere in the universe. Or it may not. The physicists who have devoted their careers to this question do not yet agree. So here you are, 60 million kilometers become 60,000, become 60, then 0, then behind you. You are inside now. The universe outside is compressing into a bright ring in your rearview mirror, playing out its remaining history at a speed you can perceive but never fully process. Ahead of you is not a place but a moment, a piece of your future that has already been written by the geometry of space-time itself, as fixed and unavoidable as tomorrow morning. You have minutes, perhaps only a few. And in that time, you are experiencing something that has been mathematically described, argued about, and fundamentally disputed by some of the greatest physicists of the last century, and that no human being has ever actually lived through and returned to explain. You are not being crushed, not yet. You are not being erased, not exactly. You are somewhere between a well-understood equation and an open question, falling through the one place in the universe where physics itself runs out of answers. The tidal forces are beginning to change. Your feet feel heavier than your head. Whatever comes next, it is already, in some sense, the only thing that could happen.